Okay, so not only machine learning AI is an interdisciplinary topic, so it has also a lot of open problems. And today we talk about ongoing work and open problems, not about results, because being the director of the department, in spite of the fact that it's very small, adds an enormous amount of mess. And so I'm still in the middle of all this. And but I'm going to conclude my mandate in 1 year and a half, so I'm very happy about that. So today I want to talk about two things. What we call liquid states in feedforward networks, and I will show you some relatively new results that give some idea of the role that this state have. And then I would like to talk about what happens in Attractor network. What is the role of these liquid states in Attractor neural network? So there are two different applications of the same geometrical structure. So just to focus on the main underlying general problem that you're trying to address, there are essentially three issues that we want to discuss. The first one is the role of overparameterization and overfitting in neural networks. So how does it happen that we have a huge system with billions and billions of parameters which generalize well? This is an important problem for various reasons. Theoretically, it's something that came unexpected. So there are a lot of conceptual challenges related to how one can overparameterize the system and still regularize it in a smart way so that it doesn't overfit the data. So this is really important because with overparameterization, you gain the fact that algorithms can converge to solution more easily, and so it's really important. There are also practical issues related to this. I just want to mention one that is, nowadays one of the obstacles for applying AI to the society is copyright, right? And copyright violation by ChatGPT, for instance. Now, the issue here is that ChatGPT is so big, GPT-4 is so big, that it actually can remember a single data point that he has seen in the data set. So it does not only try to merge the information and extract, and build a generative model that, given a sentence, continues to complete the sentence based on all the information that it has been exposed to through self-supervised learning. But it can be shown that if you give appropriate prompts, it's able to extract single data, like personal information. So this is a kind of a huge obstacle for the distribution of this kind of technology across society. I mean, there are examples of this. I don't have them here, but just to say that overparameterization is kind of it's very interesting because you mix together the capability of remembering some specific data point, but also merge them together. So I mean, it's really complicated and not at all clear. Now, with the overparameterization comes the fact that this system, I mean, this architecture are very complicated. So you have a highly non-convex system, and still first-order algorithms, so gradient-based algorithms, work pretty well. Even though here one should pay a bit of attention because these are not just greedy algorithms or just full batch gradient algorithm that work. You need to do a few things to make them work. First of all, you should use an appropriate loss function, as we will see, which tends to select appropriate solution. What I mean is that if you have an overparameterized system, clearly, as you overparameterize the system, you add more and more solutions to the problem. So, namely, configuration of the parameters such that the network is capable of implementing all the input-output association. Now, the question is then, which solution are you going to select, given that you have added a lot of solutions? So this is the issue. And this is something that, so the kind of algorithms that are used today are select certain type of solutions. Okay, that's the main idea that I will try to discuss. And then there's the issue of which kind of internal representation do this network produce, And here I would like to also mention the connection between Feedforward and Attractor neural networks. As I said, it's really work in progress. Some things are old, some are new, and please feel free to interact me because, as I said, it's not at all finished. So here, and I should say that all this is done within our group at Bocconi, and so it's not just so it's with a lot of young people. I think there's Riccardo, Marco here, and Carlo Baldassi, Carlo Cibello, Luca Saglietti, Mark Nezar, Nicola Brunel now, and so on and so forth. Clarissa Lauditi, and so on. Okay, so the kind of architecture we're going to discuss as a reference is just a multi-layer perceptron, so an architecture like this. So here you have the input, here you have the output, and then you want to, the output is computed as a composite function, and I mean, I think everybody can knows what this is. So these are nonlinear nodes, these are the weights, the W's, and so the output is given by this very complicated function, and the output is selected, the final label is selected through an argmax operation, where essentially you normalize the output to 1, and then you choose the output that has the, say, largest pre-activation. Okay. Now, the kind of function that, loss function that one tries to minimize, I mean, so the idea is that, okay, here you can see, but you have a set of examples. X mu is the input, Y mu is the desired output. And this can be, in the modern setting, the Y mu can be, say, a desired output, like say, if you want to classify images, would be the label of the object inside the images. But for instance, in the case of language models, these Y mu are pieces of the input called self-supervised learning. You take like an image, you delete a patch, and then you want to train your system to predict what you have deleted. In this way, you don't need to pre-process the data, and you can train your system. This is how language models are trained. And this has been, this is, of course, it's a very important step because most of the data cannot be processed by humans, and so you need something that is independent on the pre-processing. So now, supervised learning is quite often done to what is called self-supervised learning, where you use as labels part of the input. I mean, I'm simplifying things, but this is more or less the idea. And then you want to find, all the W's such that you do a good job in predicting the output. So you can define some loss function, which can be just the number of errors, so the number of mistakes that you make in predicting the output. And this is somehow the true cost function in the sense that you have a learning problem and you count how many errors you make. But this is not differentiable. So what people use in practice is the cross-entropy loss function that besides its probabilistic interpretation, which can be discussed, but the idea of this function is essentially that through this parameter gamma tends to favor configurations that are particularly robust. Not only you get the right output, but you get it with a certain margin. So this kind of loss function it's already a step in answering the question that I was posing before. So which solution do you select? Since you're using this kind of loss function together with regularization technique, you're actually selecting among all solutions that you insert in the problem by over-parameterization, you're choosing those that are maximally stable. So it's not just by using this, it's not an innocent step, this one, it's quite a crucial step. Okay, so now today I want to consider two basic models of non-complex neural network. The simplest one is the very famous, and I've been talking about this too much, is the binary perceptron, which is just the simplest possible architecture with binary weights, and the other is the negative perceptron. These would be prototypical models to discuss the role of geometry and non-complexity. So again, we have in this setting for analytical purposes, we have a training set which is made of random input patterns and random labels. So these are random associations. The control parameter of the problem is the number of patterns, so the number of constraints to the number of weights, so the number of variables in the problem. And the kind of and the issue that we want to be able to solve is to well, this is the architecture. So we have just one single neuron. This is the input. These are the weights. One can compute the local field of the neuron here, and then take some nonlinear function, in this case a sine function. And so the objective is to find the W such that for all the patterns in this training set, the network gives the correct label in output. This is the learning problem, which can be written as a minimization problem of a cost function. And it's more convenient to write this problem. Now, if you multiply by y, the left and the right side, here you get 1 because y is plus or minus 1, and the label enters inside the sine function. So you can write this as 1 equal the sine of this delta, and delta is called the stability. Delta is the product of the output times the local field. And you want, for all the patterns, this quantity to be positive. So you want your local field to be aligned with the input field. Okay. Now this problem becomes non-convex in two settings. One setting is when the weights are discrete. It becomes a discrete optimization problem, which is NP hard and whatever you want. So it's very hard to train. And also when you ask you modify your problem and introduce what is called a negative stability. So the normal problem would have k equals 0. So you would like all the input fields to be aligned with the output. But if you allow for some errors by taking, say, a negative value of this margin k, then the problem becomes non-convex. And so the idea is that if you have a normal perceptron with k equals 0, the problem is always convex. Imagine, you see that when you write, so the decision boundary is given by delta equal to 0, where sign changes. So this is just the equation of a hyperplane, right? So it's the hyperplane, say, orthogonal to x mu. And so in the normal perceptron, say that this is the pattern. So, and the idea is that everything is classified correctly, say, if it is below this hyperplane here. So you add one pattern, you get this hyperplane, and these are the on the hypersphere of the allowed values for the weights. Sorry, I forgot to say the binary perceptron is binary. The negative margins with continuous weights, real numbers constrained to be on the sphere just to normalize the total volume of the weights. Now, if you have a negative, so k equals 0, what happens that whenever you add one pattern to the training set, you cut this hypersphere in half, and so you say have to throw away half of the space. Okay, and so let's say that you have this pattern, and then you select this region. You add another pattern, say like this, and so you select these other pink regions, and what remains is just this region. This is the intersection of the two. So this would be the region in which both patterns are classified correctly. And this is a convex set. And if you continue like this with k equals 0, you always constrain your feasible solution to a convex set. So it's easy to train this problem. Any algorithm would work, and so on and so forth. However, if you take k negative, so if you allow for errors, what happens is that the feasible region splits into many components, and the problem becomes non-convex. So, so this problem is actually, it's easier from the point of view of, so the constraints are relaxed because you allow for errors, because you accept a negative stability. So you accept mistakes in the input. But by doing this, you introduce some non-convexity into the problem. Okay. So just to, this is a numerical experiment that Gabriele Perugini has run in the last week. And if you take a kind of a neural network with some stability k, and you test it on some real data, and you check, in this slide here is, this is Cypher 10. It's a very famous data set of images. Here you want to discriminate between bird and deers. Okay, I don't want to enter. So the input is, 3,000 pixels, and then you have a network with 1,000 hidden units and one output. And if you do this, here in yellow, you have the region in which the network is capable of finding zero error solution on the training set. And then here you check how it generalizes. So how well it performs on data that it has never seen. And what happens is quite surprising. So yellow means better, blue means worse. And it generalizes better with negative stabilities. So how is that possible? So you're making mistakes on the training set, you make the problem easier, and you generalize better. So there's and another. So this is kind of a little bit, yes. Sorry. Just look at the slice. So this gamma is actually the gamma of the loss. Is the effective temperature of the cross entropy. But this is just a provocative kind of slide. So forget about. So just take one value of gamma. Let's say for one value of the parameters of your loss function, say this, and you see that for negative k, this is a bit more yellow than in the other case. So how is that possible? Okay, so I want to answer this kind of question in the first part of the talk. So let me start to review some old results on the binary per second. So now let's, as I said, there are two cases. One is discrete weights, and the other is continuous weight with negative stability. So let's start with discrete weights and stability equal to 0. So no problem with that. And now the binary per second is very famous. It was solved in the 80s, and then there are recently a lot of rigorous results proving the result what was studied in by statistical physics, and essentially the outcome of the analysis is that in the binary perceptron, when you do random association, you have an exponential number of solution on in the weight space, and these solutions are point-like, and they're typically order n in Hamming distance far away from one from the other. So it's a kind of a golf course. And as the number of pattern P increases, so as the size of the training set increases, the log of the number of these solutions, so the entropy of the problem goes down. At a certain point, it hits 0, and that corresponds to the critical capacity. So in a binary perceptron, you can store at most 8.83 times n patterns in the limit of large n. That's the very famous result of the 80s. In principle, it doesn't mean that you can do it in practice, but this is just there exists solution up to that value. Now, this result, it's kind of basically impossible because it has to be wrong, because if this would be the case, so if the solution of the binary perceptron would just be these isolated clusters of solution, then the so-called overlap gap property that has been studied by Gamarnik and other collaborators in the recent years would lead essentially to the impossibility of training this kind of devices. So what Gamarnik has been able to show that if solutions are isolated in a technical sense that I don't have time to review today, but if then all locally stable algorithms are bound to fail. So this would be the case for the binary perceptron if the space of solution would just be the one given by isolated solution. So that, I mean, this could be true, but it contradicts the evidence. And in fact, there exist a lot of algorithms that actually find solutions very quickly for this problem. So what this means, and what we have been studying a lot in the last years, is to analyze which type of solution do practical algorithms find, and what happens is that the kind of a solution that this algorithm finds are not the point-like solutions which cannot be reached, as this theorem says, but are other solutions that are subdominant, which can be found by the algorithm. So what essentially this means is that, yes, you have this point-like solution, but there's something more, which doesn't come up directly from the statistical physics calculations because they are subdominant. So one has to go look at subdominant states. So what we have been doing in the last 5 or 6 years is to develop techniques to study rare states, so subdominant states in this complicated landscape. And in order to do this, what we have developed is the so-called a local entropy approach. So essentially, we, instead of looking to solution, we look at a constrained geometrical problem. So we ask ourselves, I want to find, we try to solve the following problem, find the regions of diameter d that has the maximum number of, contains the maximum number of solutions inside. And then we move the center of this region around the configuration space. So that's the objective that you want to solve. And, if this kind of region would be, physical states, this would correspond to the one-step replica symmetry breaking scenario, but they could very well be just regions that are not stable in a thermodynamic sense. So they could think to this just as a way, as a lens for exploring the geometry of the space of solution of this problem. And so what happens in practice is that the number of point-like solution in this problem is vast and exponentially dominating, of course, but still by using this technique, you can explore also what happens in rare regions. And this is because if you look at the entropy of this region, if you take the diameter sufficiently small and you imagine to be around one of these point-like solutions, then the log of the number of solutions would go to zero. So it would give a vanishing contribution. So this kind of approach would just would give zero weight in the statistical physics analysis to point-like solutions. So with this technique, we can reweight and give more and study the existence of these clustered phases. And of course, when you do this, you can apply the usual thermodynamic techniques, and you can compute the internal entropy, and you can compute the external entropy, which would be the complexity in the case of spin glass theory. But as I said, these do not need to be states. So let's say I can count how many regions of diameter d exist and which is their internal entropy. This is the objective. And so this can be formalized by essentially introducing a cost function, which is the log of the number of solutions inside this hypersphere of diameter d, centered in this vector w tilde. And what we want to do is to find the center of these regions. And so what we have to do is to study a new problem in which the energy is substituted by this entropy that we call local entropy, just because there is this parameter d which defines the size of the problem. So it's not, d is not equal to n, it's smaller than n. Okay, so we are kind of using this to move around and look what happens. So we have to study a new problem, which is more complicated because clearly an energy, n is the number of solutions inside the regions of diameter d centered on w tilde. So this is an exponential quantity. So we need ways to estimate this quantity. But if you can do that, then you can detect the existence of these dense regions, even though they are subdominant. Okay, one can introduce temperature and kind of write a smooth version of this, and so we can define what is called the local free entropy. But I have many things to say, so I'll try to go fast on this, but we can stop if you want. So if you apply this technique to the binary perceptron, what you find is this result, which is pretty old now, that is in addition to the isolated state. So in this plot, you see the distance from a reference solution w tilde, and here is the entropy, the log of the number of solutions. So if you look at this isolated solution, which dominates the Gibbs measure in the original problem, this corresponds to this dashed line. So here is for a certain alpha, meaning for a certain number of patterns. You see that you find at a distance 0.03, whatever it means. I mean, you find an entropy which is 0.07, meaning that there is an exponential number of point-like solution at this distance. But as you reduce the distance, at a certain point, the entropy goes below zero, meaning that there is a gap. So these solutions are isolated, just like in error-correcting codes. So you have a lot of solutions which are isolated. So you have a gap. Now, on the contrary, if now you look at these regions of maximal entropy, what you find is that these solutions do not display a gap. On the contrary, very close to zero, they become extremely dense. So this explains why, this reconciles the scenario with Gamarnik's result, meaning that, yes, the algorithm works because there exists solutions that do not satisfy the overlap gap property, so that they are not isolated, and stable algorithm can actually find them. Okay. Not only that, this just to mention that not only this solution can be found, but they also have good generalization properties. So if you generate the data using another network, it's called the teacher network, one can show that this solution that belong to dense regions generalize better. But just keep this message in mind, and then I really don't have time to discuss this. One thing that I want to mention, just because I think is useful, is that if you take this local entropy and you write it at finite temperature, you can write the partition function of the problem, say like this, where this is beta prime is the parameter which is conjugate to the number of errors, to the cost function you want to minimize, and then you have another fictitious temperature times this entropy. So this is the usual splitting of the free energy. But the point is that if you take this y, this effective temperature, you take it integer, you can write the partition function of this problem just as a partition function over real replicas of the system. Okay, just by taking this effective temperature integer. And of course, you would like this y to go to infinity to find solution of maximum entropy. So this would be like beta. So you would like to, and so if you take a lot of replicas and you sample using this partition function, then you would sample from these rare regions. Okay, and so this has led to in practice, what you can do is just take a finite number of replicas and try to sample from a replicated system in which you have a constraint of distance between the replicas. That's it. And so by taking this as a new objective, you can set up a lot of new type of algorithms, like message passing, like the cavity method applied to this, simulated annealing on this replicated cost function. So very quite known in the machine learning community is entropy SGD, which is essentially the continuous version of this. So there are many algorithms that are based on this idea. And actually, this sharpness aware minimization algorithm, which is probably the algorithm that is mostly used today in machine learning, what it does is actually to minimize, try to find solution that maximize the density of solution around the solution that one has found. So it's actually trying to sample from these regions. So again, I don't have real time, so I just want to mention this. A clear example that we did many years ago is if you just take a simple model in which you can run the cavity method and so on, you can estimate this local entropy using some in-field techniques. And so you can set up a new Monte Carlo algorithm in which you accept the move if the local entropy increases. And if you do this, all of a sudden the binary perceptor becomes very simple. Whereas if you run a plain simulating annealing algorithm, you are bound not to find solutions at all. So this would be the normal simulated annealing algorithm on the binary perceptor. This is for finite n. If you increase n, this plateau extends to infinity. Whereas the entropy-driven, local entropy-driven simulated annealing just goes down and finds solutions. Okay, so this is, and also for the expert of replicas, this local entropy formalism is strictly related to Monasson's description of replica symmetry breaking. Just at variance with respect to Monasson approach is that here you have to take the Parisi parameter m larger than 1, so it's some non-equilibrium value, so non-physical value, let's say, and you have to use the overlap of the 1RSB formalism. You have to, instead of optimizing over Q1, you have to use it as a control parameter. But if you have the 1RSB equation, you can take them and use Q1 as a control parameter and also M as a control parameter, and then you will be able to find. So there is a formal connection between these two things. And of course, if by moving this Q1, it happens that you find a maximum or a minimum, a maximum of your free energy, then it means that these states that you're looking at are also stable in the thermodynamic sense, and so this would coincide with the 1RSB formalism. Okay, so now this becomes, one can ask the following question: how are these dense regions composed? I mean, let's look into these regions. Are they just uniform regions of high density? How do they look like? Well, so this could be a little bit a little source of confusion. So what I want to argue now is that if you look inside this dense region, you find that they are composed of that inside this region there exist a lot of extremely stable solutions connected by less stable solutions. So it's a very these are dense regions are very heterogeneous and contain inside very dense regions and less dense regions. And so now in the binary perceptron, you can compute how many solution you have that are very stable. And as you increase the stability, what you find that there are less and less of these solutions. But what is interesting to observe, if you compute the typical distance between stable solutions, that they do not scatter around on the hypercube, but they get closer and closer, which means that if you look for very stable solutions, they tend to coalesce. And in fact, one can show that these dense regions, these dense regions are composed, heavy dots are solutions that are very stable. So these dense regions that have a very high local entropy are heterogeneous, and they contain inside high density regions connected by less dense regions. And if you just would like to solve the problem of finding specifically one very dense region, this would be a very hard problem. You would not be able to find it. But if you relax this constraint, you're just happy to be inside these regions and find a solution which is close to a very stable one, but doesn't necessarily coincide with a very stable one, then it becomes accessible. I don't know if this is clear, but really I don't have time, and I've already said this many times. So, but I think it's interesting. So you have these regions that are very heterogeneous. And so these two pictures, I like to repeat this. These two pictures are just the same picture. Just this done by mathematician, this done by physicists, but they describe the same object. I don't know what is the psychology behind this, but it's always amazing to look at this, how different is the interpretation of the same object. Okay, so we have now seen that if you have a non-convex problem resorting to this dense region, you can actually think of solving it, and so everything looks fine. Now the question is, how can we connect this to overparameterization? So what happens if we overparameterize the system? If we overparameterize, so one way we can do a lot of numerical experiments. We did, but I'm not going to mention them. But anyhow, one can set up the following model. It's called the random feature model. So you take an input of dimension d, you project in a higher dimensional space, like a supervector machine, where you project in a higher dimensional space. So you make a random projection from dimension d to dimension n, and d and n are of the same order. And then you apply some classifier. So you have your input pattern, you project in a high dimensional space, and then you try to classify it and obtain some desired label in output. So this one on the left with the linear classifier here is called the random feature model. So what we can do is take the same expansion in input from D to N, and then apply here a non-convex classifier and see what happens. Okay, thanks to what is called the Gaussian equivalence theorem, which is a way of computing the properties of the random variables in this input layer. So assuming that here you have independent random variables in input, which is the probability distribution of these variables, well, one can describe this, and everything happens as if these were Gaussian variables with some noise, quench noise. And so there's been sorry, here it's not written, but there are two papers, one from mathematician, one from physicists, proving this result. And so we can actually do the calculation and repeat more or less the analysis of the structure of the phase space for this overparameterized model. And what we find is the following, is that, okay, here there are a lot of parameters, but let's maybe just look at just one line. So here is a certain value of alpha t. Alpha t is just a measure of how many patterns we present to this network. So it's P over D. So the fraction of pattern with respect to the dimension of the original input space. So it's P over D. Okay, so it's number of patterns to the dimension of hidden dimension of the input. Okay, and then we can change alpha. So essentially, we can change the dimension of the hidden layer, and so we can can study what happens here. So we fix a certain number of patterns and we change n, which means we move along this line downwards, because you see alpha. N is p over alpha. So essentially, you want alpha to go to 0 if you want n to be over parameter. So you move in this direction. So what happens is that if you have a non-overparameterized system, you have no solution to this problem. Just you do not have enough parameters for fitting the data. And so essentially the landscape is like this. Now, at a certain point, you hit a transition line, which is an information theoretic line, which is called this, it's just a so solutions start to exist for a certain value of overparameterization. So if you increase the size enough, solutions start to exist. So you're in a situation like this. But if you do the local entropy analysis, you find no dense regions. So you expect that after this line, you will still not be able to find the solution. And then if you continue to overparameterize, at a certain point, high density solutions start to appear. This is in the discrete setting, okay? And so you have this double transition. One is the information theoretic transition. Then you have another transition where these dense regions start to appear. And if you check the behavior of algorithms here, indeed, what happens is that they start to find solution below this second line here. So, which means that you can have an overparameterized system, but you need this kind of dense region in order to find solutions. Okay. Now, I think I completely missed the timing. Okay, I'll try to be quick. Now, what is the continuous version of this? So which is the simplest continuous model that displays non-convexity and so on? As I said, is the perceptron with negative stability, so a perceptron that makes errors. Now, to make a long story short, because I want to mention something about Attractor network, this model has been studied in the context of jamming by a lot of people, and Silvio, Giorgio, and so on, Francesco, Pier Francesco, etc. And because it's a model for jamming, but here we consider it as a model of neural network. Now, forget about all these lines because I don't have time, but essentially what happens here is that if you choose a negative stability and then you increase the number of patterns, in this case, we do not have overparameterization, we just have the plain model. We don't have that projection layer, so it's just fixed at the moment. So you just increase the number of patterns. What happens at a certain point, so there is a region in which this dense solution exists, and then there is a transition line where these dense regions disappear, but the system is full RSB, and so you have a hierarchy of a very complicated landscape of solutions. So what happens here is that at the boundary here where the dense solution break up, the algorithms do not stop working. They continue to work. They just behave differently in terms of generalization and other property. But in the discrete setting, what happens is that when you go beyond this line, so when dense solutions disappear, you are left with just a golf course, and so you will not be able to find solution. On the contrary, for dense model, you have a multitude of states. It can be very complicated if you consider also out of equilibrium configuration. So to make, in a nutshell, algorithms continue to work, but geometrically still something happens here. Okay, and okay, so, but one, essentially, so it's no longer an algorithmic barrier, the disappearance of these dense regions, because you still have other solutions that can be found by greedy algorithms. So it's not directly related to computational hardness in this model. In multi-layer networks, it can be different, but it's still related to geometry and generalization in the sense that what happens essentially when you are here compared to when you are here, there is a paper by Enrico. I don't know where it's Enrico, but all the young guys in our group, they've studied the geometry of the solution space in this negative perceptron setup, and what they find is that below this critical line, what you have is that you have a lot of solutions that are on the boundary of these regions, so are the edges of this star, but then there is a core that is extremely dense. And what happens at the phase boundary is that the structure of this solution changes completely. And one interesting thing about this is that if you consider this as a model of a neural network, then it turns out that this negative perceptron appears to generalize pretty well if you use algorithms that go they try to go in the core of these regions. Provided you use that type of algorithm, then so here is an experiment in which you have the stability, which can be negative, and here you have the generalization error. You see that for negative stability, the red dots are given by an algorithm that goes into the core of those regions, and the generalization error is pretty small. Whereas if you use just greedy algorithm like just a gradient descent, you get stuck at higher errors. So you see you have very different phenomena depending on which type of algorithm you use. Okay, let me skip this because I'm very, very late. We have been doing this also in over-parameterized networks. So we have done now this random feature model with a negative, with a neural network with negative k. And what we find analytically is that indeed they generalize better when the error is negative, which essentially means that, going back to, I give you just the intuitive solution. So intuitive idea. With negative k, somehow you are able to enlarge the center of this very complicated region. Then, because you relax the constraints, so you will have more solutions. So somehow you amplify the contribution from these dense regions. And if you are able to find the body center of this region, somehow you find a solution that is representative of all these solutions. So you can think of this as a kind of a Bayesian local learning. And it turns out that for negative k, if you're able to go inside this region, you generalize better. Okay. Okay, I don't have time to, and this is actually the kind of experiment that Gabriele has been doing lately that I mentioned at the beginning. So now what we want to do is to apply this to deep network and see what that, because here we have just one layer, so you just have to modify the loss function. But when you have a multi-layer network, you have to induce negative stabilities also in the hidden layer. So one has to modify stochastic gradient in order to do this, and we have ideas, and we are actually doing that. Okay. There are many applications, but I'm very, very late. So let me just, since I know that a lot of you are working on Attractor neural network, I really want to mention this result on which we have been working for 1.5 years and are still stuck. But we have some results that I want to share. Essentially, we can ask more or less the following question. So we have seen that in learning problems, this dense region play a very important role. And there is some duality that I don't have time to discuss that made us think that indeed also in Attractor neural network, this could be the case. And so we have been studying this in the case of Attractor neural network. In particular, we consider asymmetric neural network. There's been a lot of work on asymmetric neural networks since 1988. There was a very famous paper by Sompolinsky, Crisalt, and Sommers. And so essentially, if you study this problem, what happens is that if the coupling constant in front of the, okay, what you have is just a spin. This is an Attractor neural network, so it's like a spin system, like a Hopfield, just like that is an SK model in which these Jij are just random variables, and you have no symmetry. So Jij is not equal to Jji, so you do not have a Lyapunov function of the dynamics. So you don't have an energy function here that is minimized by the dynamics. And this system here is totally chaotic. Okay, so you can show that essentially, if this is purely asymmetric, there are no fixed points of this equation in the large n limit and so on. So say the research has been developed in trying to understand the role of chaotic dynamics inside Attractor neural networks. And there's been more recently, the kind of model that was studied was a model in which you also have some self-coupling due to local feedback, but more or less the behavior is still the same. So this would be the autocorrelation function. So 40 years of work about chaotic dynamics, and but given the duality that I was mentioning, we actually believe that in this network there should be something else. And in fact, so we have been studying this using this local entropy approach. So now we consider this Attractor neural network with, let's say, binary coupling, but this is irrelevant. This could be just Gaussian variable, it doesn't matter. So just the second moment matters. And we study, say, the fixed point of these dynamics. But we studied the fixed point. So we look at the configuration of S such that this equation, this equation are satisfied. So these are kind of update equation for the spin system, right? And so essentially we study a cost function which is equal to the sum over all the neurons of 1 minus the S times the sign of its input field. So if all the spins are aligned with the input field, this energy would be 0, otherwise it would be positive. So we study the configuration of S such that this energy equals to 0 in the larger limit. Now, if you do this, it's oh, sorry, I don't know why. No, I must. Okay, let me go directly here. Just because it seems to me that I'm over. So if you study this, you can show, you can compute 10. Okay, I'll try to. So one can try to compute the number of such fixed points. So if you do the annealed approximation, okay, so the first order method and the second order method, you can actually find that the first order method is exact. So you can show that this result is kind of rigorous. So you find that as the self-coupling changes, the number of the entropy of the fixed points follows this expression, which is very simple. So essentially, what happens is that this is this curve here describes the total number of fixed points for this asymmetric neural network. So as the self-coupling increases, so let's assume you have an infinite self-coupling. That would mean that every configuration is a fixed point, because if you have a self-coupling goes to infinity, every configuration should be a fixed point. And in fact, this entropy goes to log 2. So everything is a fixed point. But if you reduce the self-coupling, it goes down, and it goes to 0 when the self-coupling is 0. Okay, so this fixed point exists, but what is the caveat here is that if you take one of these fixed points and you perturb it, then it's totally unstable. So these are totally unstable fixed points. So essentially, this network is chaotic unless J is very, very big. But so there's a whole region here of small self-coupling in which this network is totally chaotic, and then it becomes non-chaotic, but just for trivial reasons. Non-chaotic just because it implements the identity or the dynamics, just the identity operator. So here, let's say the problem is trivial beyond this slide, but in this region, which is the interesting one, it seems to be totally chaotic. However, as I said, this should not be the end of the story. And in fact, if you analyze this problem looking at the large deviations, so looking at the existence of dense regions, what we do find is that this region exists. And in fact, there exists an exponential number of stable fixed points that have been completely ignored in the literature since '88, which have some very interesting computational capabilities. So this is a new way of looking to okay, I don't have time, but to neural network. So essentially, the phase diagram goes as follows. I skip the technicalities. So for J small, as I said, for J big, self-coupling big, the problem is trivial because everything becomes a fixed point. But if J is small, what happens is the following. So for J very small, around 0, you have this point-like solution, and then you have some very, very small clusters, which have a diameter that has an internal overlap, which is 0.998, something like this. So they are very, very tiny, even though they are not point-like. They are extensive but very tiny. They satisfy the overlap gap property, so there's no hope with a stable algorithm to find this solution for very small J. Then there is a critical value of J, beyond which you start to have these liquid states. And these liquid states, so essentially, you have to imagine that you have a kind of you can think of this more or less as the star that I was showing to you, even though here is a discrete setting. But so you have this liquid state that contain regions that are denser in solutions and that are connected. And so this phase, it's you have to imagine the following, that this can be used for computational purposes. So the first result is it's not true that these networks are totally chaotic. They do have these non-trivial states. Now, the question is, how do you find them? Well, in order to find them, you have to use a non-trivial dynamics. If you just use the dynamics Si at time t plus 1 equals the sign of the input field, it doesn't work. It's going to be starting with a random initial condition. You just behave chaotically. But if you modify a little bit the dynamics, you can write down local, fully local dynamics that ends up in this configuration. So the idea would be, maybe if we try to simplify a bit the topology of this system, we can find a simple dynamics that is actually capable of going here. And also maybe we can also think about modifying that learning as a way of exploiting the existence of these states. So just to give you an idea, so one way of using this network is the following. Suppose that you take an external message, an external field, which would be an external signal arriving to this attractor network, and you use it as a bias for finding solution. And then you converge to one of these fixed points. So what this would correspond to is the following. So given an external signal, you want to find the internal representation of this network that belongs to this liquid state that is as close as possible to the external signal. Well, one can show numerically that using an appropriate dynamics, you can actually do this, and you can find an exponential number of different internal representations that are highly correlated to these input patterns. Not only this configuration here do have some error correcting properties. So they are stable even under the simple dynamics. So this is a computational aspect that I think is pretty useful. And we are actually, so here I skip, sorry for I think this can be used for computational purposes. Now, what we are trying to do right now, but we have not succeeded yet, is to set up a learning scheme that exploits these dynamics and to simplify a bit the structure of the network, the random network, so that a very simple dynamics can actually exploit these states. So, as you probably know, realistic networks are not symmetric in general. They have just a component of symmetry, but they're not symmetric like the Hoffing model. So I think this is much more realistic in many aspects. And I think that the idea of having all these internal representation that have kind of error correcting properties. So this is a kind of accessible code. For those of you who know about error correcting codes, you know that in error correcting codes, you have the error correcting codes can be thought of as a kind of spin glass with ground states that are point-like, such that if you start sufficiently close to the ground state, you converge to the ground state and you correct little errors, say. But if you start from random initial condition, you will never be able to find one of the coordinates. In this model, on the contrary, you can start in an arbitrary with an arbitrary configuration. I mean, the external field can be whatever you want, and you always converge to one of the internal representations. So it's a code which is at the same time accessible from arbitrary external input. So I think it should be interesting. And I also want to mention a connection with deep networks, which is the following. Suppose you take a network. I think it was studied either by Giulio, or by, I don't know, like a cylinder, a network which is always with the same size. And then, I don't know, we together, yeah, okay. So, if you take this network and you train it, maybe skip connection, but that's a technicality. And then you take one layer and close it. And so you think to these layers as the iteration of dynamics. What happens is that the dynamics is always chaotic. It's always chaotic, even after learning. So somehow it is as if this deep network implements a divergent dynamic, which is kept under control by the architecture after many layers. Now the question would be, what happens if instead you would use an update dynamics for this layer such that, yes, you have a divergent dynamics beyond a certain distance, but below certain distance you have these error correcting properties. So can the network exploit error correction automatically somehow? So this should be checked, and we are trying to implement this in deep network. So just to find a connection. Okay, I think, sorry, I told you a lot of things, but it seems to me that, well, this is a general message for statistical physics. It seems to me that this out of equilibrium states, these dense regions are relevant in many contexts because they are accessible by simple local algorithms and have good computational properties. And okay, I'll stop here. Thank you. Yes, Federico.
So you're counting fixed points, and then you say some are accessible and some are not.
Yes.
How do you define? So you're not counting the phasing of that, right?
No, no. When I say accessible, I mean I skip this part. But if we write down say the cavity equation that come from the large deviation analysis, they converge to this fixed point, and then you can check that there are also fixed points for the simple update analysis. So the whole part that I didn't have time to mention, but you can show that you, I mean, pseudo-analytical in the sense of single samples that you converge using appropriate cavity equation that can be simplified and made totally local. At the end of the day, each neuron just looks at its input signals and updates its state. That's it. Even though it's a bit more involved than just the.
So they correspond to stable fixed point of the.
And not only, and also of the updated. So these are different type of equations that have the same fixed points, but those that you find are actually stable also for the simple dynamics. Just that by using the simple dynamic, you would not be able to converge from random initial condition, whereas or random external fields, whereas using these other dynamics you can.
So I have two questions. One is on this part. So it's a curiosity. So in principle, on this asymmetric case, you can tune the asymmetry and you can go from symmetric to. What happens to the liquid state when you tune the?
I'm doing that. We just started to discuss with Nicolas Brunel about this. The way of doing this is, I mean, these models are not very realistic because you would like to have neurons that are either active or silent. So 0-1 neurons, and then you like to split them in excitatory, inhibitory, and make it a little bit more realistic to also to define what symmetry really means. Because in this model, symmetry, even if it doesn't make a lot of sense, but yes, it's definitely it's a bit more complicated because the JJ become more correlated. But this is something we are working on. It's a very good question. Exactly what we are doing.
And the other question is on the first part. When you train the reducing neural network, the loss. So a long time it goes close to zero and then stay for a long time close to zero. And in this time regime is where the system during the training starts over. So I'm wondering if you have an interpretation of the fact that it looks like that in the dynamics, the system, I mean, when it goes down at the beginning, reach this white flat, but then if you keep going during the training, it moves in the white flat, but in regions which are at worse generalization property.
Yes.
So you have an understanding. I mean,
yes, yes, because it's like you let it diffuse, and so the probability of going in one of the, let me say, let's use this analogy of the star-like shape of these regions, right? So if you just do perform a kind of a random walk, then you're going to diffuse in one of the branches of the star. So you're not confining yourself to because they have more entropy. So that's the more or less the naive interpretation. But that strongly depends on which kind of dynamics you use. So if you would use a dynamics that targets exactly this region, if you use a percentage, you have that problem because it tends to go to infinity, and so to minus infinity, and so you never stop. But if you use a dynamics that just wants to maximize the local density for a given D, you actually stop. Yes.
But when you're in a branch of the star, don't you tend to come back?
No, because well, I don't have any. I just have numerical results on this, but essentially you diffuse and you move in one of these.
And then you stay there.
Yes, yeah. I don't have a precise result, but that's just the intuition. I don't have a precise answer on that. It should be studied more carefully, but that's the intuition. Yeah.
We have time maybe for a very question.
It's a technical question. I was quite intrigued by the negative margin.
Yeah.
I was just going technically in the deep net with continuous weights. How do you inform that the function is not collapsing to zero? If the function is zero, it means your data.
You mean with the value transfer function?
Yeah, I mean, if you, I mean, don't you take a negative margin for the loss?
Yeah.
So if your function is zero, then it will put data, right?
No, it is as if you would accept a little bit more, accept some errors. So it doesn't, I don't see why it should be like that. I mean, it's just if essentially, if a pattern is sufficiently close to some other pattern that is classified in a certain manner, then you classify it in the same way, essentially. So you accept a little bit of errors. So you're not driven to zero. That's does not depend on that. Okay, thank you.